Hello everyone and welcome back to EECS 2200. Today we're going to continue our discussions and start chapter 6, which is basically an introduction to inductance, capacitance, and mutual inductance. And we're going to learn about these components and how to deal with them when we have circuits that include these kind of components. Okay, so let's go ahead and get started with the inductor first. It's a two-terminal device. I'm sure that most of you have seen the symbol before. It's basically looks like this. It's a two-terminal, so similar to a resistor, and it's representing different kind of ways that we can actually implement an inductor. So we could implement the inductor using, well, this method or the one on the left or the middle, right? It doesn't really matter how do we implement it. Similar to resistors, it didn't really matter how do we implement resistors, what kind of material we use for resistance. What we care in this course is basically how much inductance do I get, right? Similar to resistors. So for example, for a resistor, we said that it's a two-terminal device. This is the symbol, and I'm going to call the resistance R. And if this is the current, and the voltage is in the direction of, basically the voltage drop is in the direction of the current, V is going to be equal to Ri, right? So here's the same story. So I'm going to say if this inductor has an inductance L, and I've defined V and I the way I've defined here, V is going to be equal to L di over dt, meaning that, well, first of all, it's not a linear relationship anymore, and the voltage is actually basically related to the rate of current variations with the time, not with the actual magnitude of the current itself, right? Of course, from math, we can tell that if I have the top equation, I can write I based on V. So if V is L times the derivative of I over with respect to time, I is going to be 1 over L times the integration of V over time, of course, plus an initial current. So that tells us, this initial current tells us that if I have the expression for I can find the expression for V, because I just need to do the derivative and then multiply that by, take the derivative and multiply that by L. But if I have V, I cannot find I if I don't have the initial current. So I also need the initial current as well, okay? So just a couple of observations from mathematical point of view. Now, knowing that I have a V equal to L di dt, I can make two very important observations about the behavior of an inductor, right? The first observation is that V is equal to, let's write it down here, di over dt. So it is related to the variations of I, not the I itself. What does it mean? So if I is constant, then what do you think is going to happen to V? Well, if I is constant, if I have a constant current, meaning that, let's say that I have a circuit that all the voltage sources are DC sources, meaning that they're basically constant numbers, like 5, 2, negative 17, or 532, right? So as long as it's a constant value and nothing is changing in the circuit, well, the current might be anything. I'm going to find it, but then the current is going to be constant. The moment that I know the current is constant, I know that, well, di over dt is going to be what? It's going to be 0, right? Derivative of a constant value is 0. Therefore, no matter what is the inductance, no matter what is the L, my V is going to be 0, okay? So it doesn't really matter if I have 1,000 turns here, or like 1,000,000 turns, or like the thickness of this metal. All of these parameters could change the inductance, by the way, right? So how many turns do you have? What is the spacing between these turns? What is the thickness of the material? What kind of material you have? All of these things could change the inductance, right? But as long as there's a constant current flowing through these wires here that I basically turned into the shape of a coil, I'm going to get a voltage equal to 0. And it kind of makes sense, because if you think about it, at the end of the day, this is a wire, right? It doesn't matter how do I shape it, it's a wire. As long as it's an ideal wire, as long as I have assumed that there's no resistance in it, it's a wire, it's an ideal wire. So if there's no reason for us to have for an ideal wire, we know that there's no reason, if it doesn't have any resistance in it, it's not going to have any voltage difference across it, right? It's like a piece of wire that I've turned into something else, but it's still a piece of wire. So the voltage across this is going to be zero unless the current is changing, right? So if the current starts to change, then something will happen, and you've learned that in the physics course, that you're going to have a self-inductance. When the current is changing, you're going to have basically that the changing current is going to build a magnetic field, that the magnetic field is going to basically induce a current into induce a voltage across this coil, and that voltage is what we call that voltage is basically what we have here, the voltage across the coil. So it's basically the self-inductance that causes this voltage, and the self-inductance really comes from changes in the current variations, not the actual magnitude of the current. Okay, so you need some sort of a varying current to have a voltage across the inductor. Okay, so that's the first observation. The second observation is that, again, looking at this L di over dt, I can see that if I have an instantaneous change in the current, I mean that if the current changes by a finite value at zero time, like the current was 2 milliamp or 2 amperes right now, and then in zero time, in a moment after now, it's now 10 milliamp or 10 amp or any other different value, right? If I have a finite change in zero time, what will happen? Well, if I look at this mathematically, I can see that this di over dt, if I have an abrupt change in the current, let's say that this is my I, and this is time. So as long as the current is continuous, we are fine. Like, let's say it's increasing, then it's decreasing, then it's constant, then it's decreasing, and then suddenly, and then let's say like it's constant for some time, and then suddenly it jumps up to another value, right? And this jump doesn't have to be big. Let's say it's even this much, right? And then it's increasing again, for example, right? So what would be the voltage across this inductor over time? Well, if I look at this from a mathematical point of view, I would say that, well, for this section, I know that the voltage is basically the derivative. Let's say L is 1, just for simplicity. The derivative of the current. So the slope of this line is positive, so I'm going to have a positive voltage. Then I'm going to have the slope is 0, so I'm going to have a voltage equal to 0. Then I'm going to have a negative voltage. And for this section, I have again 0. And for after that, I'm going to have a voltage that is positive. The problem is exactly at this point, right? At this point, the di over dt is infinity. So my voltage has to be infinity. So this has to go to, well, I went a little bit too far. To infinity, right? And that's the problem. So we cannot have an infinite voltage in a circuit. Because we cannot have an infinite voltage in the circuit, you can imagine that we cannot have an abrupt change in the current of an inductor. We can have an abrupt change in the voltage of an inductor. You can see that, like, I do have abrupt changes, right? But for the current, I cannot do that, right? Because the di over dt is v, dv over dt is not I, right? So cannot have instantaneous change in the current. And by instantaneous, we mean finite change in zero time. Okay. Now, you might think that, well, in practice, let's say that you might think that, well, let's say I have this circuit. I have a voltage source, resistor, and then an inductor. And let's say I have a switch here. And initially the switch is closed, right? So it's connected. So R, L, and these two are in series, and there's an I flowing here. And let's say I have this voltage, right? Now, you might think that, well, you have a current right now. What is this current? Well, it basically depends on the value of V, R, and L, right? But you do have a current. And then you know that the moment that you might tell me that, well, if I open the switch, then I have an open circuit. So the current has to be equal to 0. So the moment I open the switch, the current becomes 0. So I do have an instantaneous current change. I had a finite value for current, let's say, like, I don't know, 3 amps, 3.2 amps, or some random number. I had a current, and now I don't. So I did have an abrupt change in the current. Well, in practice, yeah, you might think that you're actually changing the current abruptly, but if you actually look at what happens if you go to the lab, and if you actually, well, don't do it at home, but if you have actually observed this, when you open the switch and you had a current and then you suddenly open the switch, you might have seen a phenomenon called arcing. You might actually see a little spark in the switch, right? You might actually see a little bit of spark for a moment in the switch before everything turns off. And that spark is basically when you open the switch, the electrons the current cannot go to 0 abruptly. So what happens is that the current wants to decrease and then wants to go to 0 in a short time. So what happens is that the electrons are actually jumping over this gap. So you're going to have electrons, or, well, basically electricity carriers, right? Whatever you're comfortable with. You're going to have electrons jumping over this gap, and that's why you will see those sparks. You will see something that is called arcing. There's an arc between the two sides of your switch, and then that happens for a very short amount of time until, well, the current of the inductor comes to 0. But you're going to see that, right? So with the normal switches that you have at home, there's enough safety and protection that you won't be able to see that, and that wouldn't affect you. But then if you look at the old switches or the things that people make, the circuits that people make in the lab, you will be able to see that. Or even, like, you can actually take, you don't really need to have a switch here. You can have two pieces of wire and bring them close enough to each other, and you will see a little bit of spark between them, because the electrons want to jump over, or like if you have these two connected and then try to actually disconnect them, if there is enough current there and you want to disconnect them abruptly, you're going to see those sparks. Okay, so back to our two observations. Number one, when you have no current variations, there's not going to be any voltage. So the inductor is going to be just a simple piece of wire. Number two, you cannot have an instantaneous change in the current. Okay, so the current of an inductor, you cannot have an instantaneous change there. Okay, so the other component that we want to talk about is capacitor. Again, I'm sure that all of you have seen this symbol. Basically, capacitor is made of two pieces of conductors that are separated with an insulator. That insulator could be just air, just an air gap, or it could be different kind of insulators depending on the size of these the conductor plates and the distance between them and the type of insulator. You might get different kind of capacitance. And then you can imagine that if you go to the lab or if you go to an electronics store, you will see that there's so many different kind of variations of how people implement the capacitance. Again, for this course, we don't care about too much about the difference between these types of capacitance and how they're built. What we care about is, well, it's a two-terminal element, electrical element, and if we show V and I the way I've shown it here in the left, this time I is equal to C dV over dt. meaning that the current of a capacitor is equal to its capacitance times the rate of voltage variations, or the derivative of voltage with respect to time. Okay, so what does that mean? Again, we can make two observations. Number one, if V is constant, so if V is constant, I can tell that, like, for example, again, imagine a circuit with independent or dependent sources that basically all the numbers are constant. There's nothing that is changing there. There's nothing that is function of time. By changing, I mean something being function of time. For example, instead of voltage being 5 volts or 2 volts, we have a voltage equal to sine of omega t or sine of 10t, right? It's a function of time, right? So if nothing is function of time, the voltage is, if the voltage is constant, then it means that the current is going to be 0. Okay, mathematically looking at this, dv over dt, so let's write it down. So dv over dt is going to be 0, therefore I is going to be equal to 0. And again, it does make sense if you look at it from an intuitive perspective. You have two pieces of conductor here and here, right? If you have a constant current flowing here, well, this looks very much like an open circuit. There's no reason for electrons to actually jump over this gap, right? You just have basically an open circuit between the two sides. So yes, if there is nothing like changing here, if the voltage across this capacitor is not really changing, for a normal circuit, this is an open circuit, so there's not going to be any current. So this branch is going to be an open circuit. So that's why with capacitors, by the way, we have, you might have seen this symbol for capacitors as well. So the other plate doesn't have to really be a curved one. It could be just two straight lines. With capacitors, we really, if it's not a varying voltage, if it's not an AC, or basically if it's a DC circuit, if everything, all the voltages and currents are constant, any branch that includes a capacitor is an open circuit branch, right? But if we have changes in the voltage, we're going to see some current flowing through that capacitor. Okay, so that's the first observation. And the second observation is very much similar to what we had with the inductors. So we cannot have instantaneous changes in voltage of a capacitance, or VC, right? The voltage across a capacitance. So this is VC. So, or let me show it here. Why? Again, if we have that, the dV over dt is going to be infinity, and that means that I has to be infinity, which is something that is not going to happen. Okay, so I've shown this picture here because if you have a charger, especially the older one, you might have seen this kind of LED on the charger that basically it's an indicator if the charger is connected to electricity or not. When you turn off the charger, when you unplug the charger from the wall outlet, you might have noticed that this LED doesn't go off, doesn't actually turn off immediately. It might take, depending on how much capacitance you have in there, it might take you a few milliseconds, like a fraction of a second, or it might even, in some cases, I've seen 1 or 2 seconds, right? It just basically fades away. The light just goes down and then becomes off after a few moments, right? The reason for that is that there are some capacitors in there that are discharging, and then it takes some time for them to fully discharge. And as long as they're not fully discharged, and they're like basically with the capacitor, what happens is that you have a bunch of, you might have learned, you definitely have learned that the way it works is that you have a bunch of negative and positive charges on the two plates, and that's how actually it works, right? So these charges don't go away immediately, right? That's why we cannot change the voltage of a capacitance immediately. So as long as you have some of these charges left, you might actually have that LED, that little light on the charger or any other electronic device that you have on for a few moments. Okay, So it's like basically a practical perspective into this. But these are the two important observations that I want you guys to remember about capacitors. So we have two kind of golden parameters for inductors and capacitors. One is IL, and the other one is VC, the current of an inductor and voltage of the capacitor. These are two parameters. I'm going to call them golden parameters because I want you guys to remember. Nobody calls them really golden. Like, you don't want to mention that into other electrical computer engineers, but like special parameters, right? Like whatever you want to call them. So these two, they always have continuous values, so no abrupt changes in them. And we're going to use this property a lot in the chapter 7 and chapter 8 when we actually analyze circuits that have inductors and capacitors. That's why I try to actually emphasize on this over and over. So it's not the voltage of an inductor or current of a capacitor. It's always current of an inductor and voltage of a capacitor. These two parameters, they never change instantaneously. So you can actually always count on their continuity, that if you had a current of an inductor equal to 2.1 amperes now, you can count on that inductor to have the exact same current a moment from now. You can be sure that the current is not going to change in a moment, like for example before or after switching, right? This is something you cannot say about a resistor. You cannot even say about the voltage of an inductor or current of a capacitor. You can only say this about the current of an inductor and the voltage of a capacitor. I hope this was clear.